In this video, I'm going to show that if a function is differentiable, then it implies that it's continuous. So to show that, we do the following. What does it mean for a function to be continuous? So let's say you have a function f of x, and let's say it's continuous at some point a. So what does it mean? It means that limit x approaches a, f of x is actually equal to the value of the function at point a, or f of a. Now, this, by the way, is the definition of continuity. Now, we are going to kind of play around with this thing. So let's say if I were to kind of rewrite it, this means that is going to be limit x approaches a, f of x minus f of a is equal to 0. Showing that f is continuous is equivalent to showing that this is equal to 0. That means limit of f of x as x approaches a minus f of a is equal to 0, which by the way is the same thing. So this is more of a useful format for our purpose. So we kind of want to show that, we kind of want to start off with this left hand side and show that it's equal to actually 0, which is equivalent to showing that the limit exists, or equivalent to showing that limit x approaches a, f of x is equal to f of a. So let's start off with the this left side, limit x approaches a, f of x minus f of a, that by the way is equal to limit x approaches a, f of x minus f of a divided by x minus a. Do you see this kind of looks like the derivative? Since I have divided by x minus a, I kind of want to multiply it by x minus a as well. All right, and note that x minus a is non-zero here. This is the same as limit x approaches a times f of x minus f of a divided by x minus a times limit x approaches a, x minus a. Because remember, the limit of the product is the product of the limits. But this is nothing but f prime of a, which is some fixed number, right? Times the limit of x approaches a, x minus a. As x gets arbitrarily closer to a, then x minus a approaches 0. And in the limiting case, this becomes 0. So this is going to be 0, which is telling me that this guy is actually equal to 0. This is exactly what we were looking for. So when this limit x approaches a, f of x minus f of a, if we show that, or which we have done, that is equal to 0, it is equivalent to showing that limit x approaches a, f of x is equal to f of a, which tells us that the function is continuous at point a, given that it is differentiable at point a. So we just showed that differentiability implies continuity. However, the converse is not true. That means if a function is continuous, that does not necessarily imply that it is differentiable. And a classic example is f of x is equal to absolute value of x. This function, this absolute value function, is perfectly continuous everywhere, including the point x is equal to 0. Okay, where it's continuous. It's a V-shaped function, as you know, if you graph it. Now, at this point, at the origin, let's say, at the origin, it is continuous perfectly. However, it's not differentiable. I hope that this discussion was helpful. Thank you very much.